So hi everyone, here's me talking about Yocto Project. And this is going to be a bit of a hands-on, well not my hands-on actually, not yours, but it's going to be a live demo because what I want to do is to show you, not only talk about what Yocto is, I want to show you how it works, and I want to persuade you that Yocto is not at all scary, like everybody said it is. So let's see how this goes. Skip that. Right. So these are the topics. So I'm going to start off with just a general chat about Yocto and embedded and why we need it. But the main thing I want to talk about is how do we use Yocto to do something useful? And I'm going to build some images and run them on my laptop using the QEMU emulator. And just to prove that I'm doing something slightly unusual here, I'm going to be using an ARM-based emulator. So we're going to be running ARM 32-bit code. Let's talk a little bit, though, about embedded and what this is all about. So these are the sorts of hardware that we're going to be running Linux on, and in particular, embedded Linux. So we have, first of all, what I call commodity hardware. So this is stuff that you buy and you kind of plug and play. The most obvious thing here would be a PC. All PCs are, roughly speaking, the same. So they're x86 based, they have fairly powerful processors, but they're quite expensive and quite power hungry. So they're not suitable for every job. We have things like Raspberry Pi. So Raspberry Pi is also commodity hardware. You can buy it quite easily. Well, used to, actually. They're out of stock at the moment. But it's pretty much plug and play. You plug it in, plug some keyboard and whatever in, and you've got a working system. And you can use Raspberry Pis for embedded use. Hopefully not the Pi itself, although I do know people who do use off-the-shelf Raspberry Pis for embedded. But they do a thing called the compute module. The CM stands for compute module. That's essentially an industrial strength Raspberry Pi. So in these cases, you can use standard distros, and it should pretty much work. Then we have bespoke hardware. So by bespoke, I mean custom design boards. And actually, this is the majority of what embedded really is. So why do we go to the trouble of designing our own computer board when there are computers readily available? And really it becomes, if you have large enough volumes, it's actually cheaper to manufacture your own boards and customize them to exactly your own requirements rather than buying off-the-shelf boards. So to a certain extent, it's a question of volume and economics. These things, for reasons of cost mostly, tend to be based on ARM-based systems. Although RISC-V is another architecture that's been around for a while, but it's really catching on over the last 2-3 years. So I expect, when I do this presentation in a couple of years' time, I'll be putting RISC-V up there alongside ARM. And then there's something in the middle, which I call semi-bespoke. So this is SBCs and SOMs. So an SBC is a single board computer. In other words, it's basically everything you need on a board, and you plug in some peripherals and away you go. And in that sense, a Raspberry Pi is a single board computer. And there's also SOMs, system on module. So with the system on module, you have a little module which contains the processor and all the expensive parts. And then it has a connector at the bottom, and you plug it into a baseboard, and that baseboard then has your custom electronics. And the advantage here is that the SOM has the expensive multi-layer board, so 10 layers, 14 layers, or whatever. They're quite expensive and quite tricky to manufacture. And then the baseboard has the cheaper electronics running at lower frequencies and doing the custom stuff you need. So it's a halfway house. It's great, again, for fairly low volume systems where you don't have the in-house resource to do a CPU design. So, yeah. So PCs were very great, but not really flexible enough, too expensive, too power hungry for the majority of applications. So we end up using ARM SoCs. SoC is a system on chip. So essentially that's a CPU and lots of peripherals integrated onto the same package. So the peripherals will include typically a GPU, USB controllers, RAM controllers, flash controllers, I2C, loads and loads of different interfaces just ready to go. So you want to run Linux on this thing, obviously. So what are you going to do? If it's a commodity system, then probably somebody's already implemented something like Debian to run on there, or Ubuntu or something. So it's quite common with commodity hardware like x86 and Raspberry Pi to use just a standard distro. But if you're not using that, then you've got to make your own distro somehow. So you could actually sit down and port Debian to your hardware. Turns out that's a non-trivial exercise that most people wouldn't want to do. So instead, we have these systems like Yocto, which will allow us to generate a distro to our own requirements. Which brings me on to Yocto Project. So Yocto Project. So this is basically a set of tools that will allow you to generate a Linux distro. So if you go look at the Yocto website, it says somewhere on the front page, Yocto is not a distro, but Yocto allows you to create your own distro. So with Yocto, you feed it some rules and specifications of what you want to build, and then you set it building, and then you come back 3 or 4 hours later, hopefully it's done what it had to do, and you now have some images which you can just flash into your system or put into an SD card and boot your target device from. So Yocto is used in many, many things. You use Yocto every day, even though you don't realize it. So just as an example, these actually are also open source projects, which in turn are based on Yocto. I put this up here because, well, partly because there's nice logos I wanted to use. So WebOS. WebOS is used for lots of things. In particular, it's used by LG for their smart TVs. So if you have an LG TV, it's running Yocto. Automotive-grade Linux. That also is based on Yocto. It's used in the head units of vehicles, especially the Japanese manufacturers, particularly like this. So if you have a Toyota, you're running Yocto in your entertainment system. And the one you can't see because of the lighting is called Onero. So Onero is a fairly new Eclipse-based project. And it's oriented towards this IoT, Internet of Things idea. And it has integration with Zephyr, which somebody was speaking about yesterday, and also with Yocto Project. The Yocto part of it typically is used as a gateway, and the Zephyr part is typically used for the remote sensors. And, oh, just back to that. Yeah, so how many devices are running Yocto in the world today? Well, the answer is nobody knows because nobody actually counts. But a rough estimate, I would say 100 million plus. It's, you know, there are more things running Yocto than, okay, I wish I hadn't said that now. I was trying to think of an analogy that's roughly 100,000, but I can't think of one. Imagine something. A little history. So actually, knowing a little of the history does help in this case because it helps explain some of the terminology, which the names of things have kind of got mangled a little bit over the last few decades. So Yocto started off actually as a project called Open Embedded, 2003. Now, for those of you who remember 2003, that is the time at which it became possible to run Linux on mobile devices. So 2003, we had the Compaq iPac, we had the Sharp Zorus, and we had the SimPad by whoever made the SimPad, I don't remember. So these are all handheld devices, ARM processors, ARM SoCs. I think they had typically 4 or 8 megabytes of RAM and a few megabytes of flash memory, which at that time was ample to run Linux. So there's a whole bunch of people hacking around with this stuff and producing Linux distros to run on these. And they came together 2003, pooled all their resources, and they produced Open Embedded. Now, it turns out many of the problems that they had solved were also relevant to more traditional embedded devices. So not just mobile, but just anything that has constrained resources. Next interesting thing is, around about the same time, there was a British company called OpenHand. And they had a contract, amongst others, with Nokia to help with the software for the Nokia N770 WebPad, which if you've ever had one of these things, it's a really nice little device. It's an iPad before iPads existed. The guy who was working on that is a guy called Richard Purdy. And one of the things he did is he created a fork of Open Embedded. And he started doing QA and kind of managing it a little bit because Open Embedded was kind of chaotic at that time. So he produced a stable version of Open Embedded and he called it Pocky Linux. And a lot of people actually, myself included, switched to using Pocky Linux because it was guaranteed to work from day to day, whereas Open Embedded typically didn't. Somewhere along the line, OpenHand got bought out by Intel for some various technology they had, but Intel weren't really interested in Pocky Linux. So 2010, they came together with Linux Foundation and they spun out what used to be called Pocky Linux and they called it Yocto Project. So the key thing to remember here, we have 3 different names basically for the same thing. We have Open Embedded, we have Pocky, and we have Yocto. And those names get rather confused because even the people who work in those areas use them somewhat interchangeably. Oh yes, Pocky. Pocky is a very tasty breadstick and chocolate-based snack, popular in Japan and other places. And Richard tells me that it is definitely pronounced Pocky, not Pokey. A lot of people pronounce it Pokey, doesn't really matter, but the official pronouncement is Pocky. So now we have Yocto Project. It has a stable release cycle now. It releases twice per year on a 6-month cycle in, roughly speaking, April and October, although sometimes they're maybe a month late. So these are the most recent versions. There are more, but they wouldn't fit on the slide. These are the most recent versions. Now, over here on the right-hand side, you can see the status. So each version is maintained by the developers for 12 months, and then it's end of life. So these are all marked EOL. But every now and again, they choose a version that will have long-term support, LTS, and they are supported for 24 months. Still not a huge length of time, but hey, it's an improvement. Okay, so that's a little bit of the background on Yocto and why it exists, and a little bit about how it's managed. So let's start off then by getting a copy of Yocto and doing something with it. So Yocto you can get by doing a git clone as shown here. There are also tarballs you can download, but it's simpler to use a git repository. And with a -b option, you specify the version. Notice the versions are given using code names such as Kirkstone, not the version numbers. I find this kind of annoying because it means I've got to remember both the version numbers and the code names and remember which one is which. Anyhow, so I do a git clone -b Kirkstone, which is the latest version, and I get about 250 megabytes in the Git repository, of which 55 megabytes is actual code, and the rest is just the Git history. So Yocto is actually quite small. That's because it doesn't contain any source code. It just contains the metadata, the rules on how to build source code. You have to do a little bit of mucking around to get the environment set up. So you have to initialize your shell by sourcing this script in order to set up various variables and other things that are needed by the Yocto build system. So you begin by doing source OE init build env, and optionally where it says build dir, you can give the name of a directory where you want to create your project. If you don't do anything, it defaults to build. And then it will create a directory, by default called build. It will cd into that directory, so that's now your current directory. And it will create a couple of configuration files which you can edit to set up exactly what you want. One thing that people often forget is you have to do this every time you come to Yocto with a new shell. So yeah, you always need to source OE init build env environment for every new shell. And what do you get? So this is the kind of layout you're going to end up with. So here is the top level. So if you just do the git clone without giving any directory name, it's going to end up being called Pocky. Again, you can see the confusion here. Really, it should be called Yocto, but it's called Pocky. Then there's the build directory we just created. These are the configuration files, which I'm going to look at in a moment or two. And then here we have, in this case, 3 directories called meta something. So these are meta layers. And I'll describe what layers are about in a few slides' time. So in your conf directory, you have bblayers.conf, local.conf. So bblayers.conf is just a list of all of those meta layers. And you'll start off with the 3 we just looked at. And then local.conf is additional configuration. So here we're going to set the machine and the distro and various other things. Here's a diagram which is meant to show how this all links together. So here's the bblayers.conf file. That is literally just a list of directories which contain recipes. So meta and metapocky are examples of that. And then within these meta layers, we just have a shoal of BB files. So BB stands for Bitbake, which is the build tool, and these are Bitbake recipes. So each one of those BB files is going to create some kind of buildable artifact. In this case here, it's going to build glibc, the C library for me. So BB layers is pointing to my layers, and then local.conf, that is the local configuration, which includes things like the machine and the distro that I want to base my build on. So this brings us then to 3 central concepts to Yocto: the distro, the machine, and the image. And these are kind of 3 variables. You can change them independently of each other, which is quite neat. So let's just go through them. So the distro is how do I want to put my system together? So the distro is a configuration which sets some policy decisions. So it will be things like, do I want to use the latest version of every library, or do I want to be more conservative and use older, more tested versions? Which init manager do I want to use? Do I want to use systemd or system5 init or some other init daemon? Policy decisions of that sort, which then apply to everything you build. Most of the time, you don't need to fiddle with the distro. So at least for beginners, you can ignore distro and just leave it as the default, which is called Pocky. Then machine, this is a pointer to the board you're going to build for. So machine is going to be Raspberry Pi or BeagleBone or any other of the machines that are supported. So that's the hardware. And then image is really just a list of packages that I want to build. So it's the list of all the things I want installed into my image, and therefore will be available to me at runtime. So just to quickly clarify that, then distro you set in your local.conf with a term like this, distro Pocky. I'm not going to go into the question mark equals bit. One of the interesting things about Bitbake is it has 10 different ways of assigning variables. This is one of them. I'm really not going to go into that because we don't have time. Then for machine, you select the machine you want to build for. So machine, BeagleBone, Yocto in this case. This actually is referring to a file. So that is actually referring to a configuration file called BeagleBone Yocto, which in this case would be in this meta layer. And actually the same with I was meant to say this with distro. The name of the distro is just actually a configuration file. So somewhere in a distro directory, there is a pocky.conf. And then we come to the tool that does the building, which is called Bitbake. So Bitbake processes recipes and also the contents of these configuration files. It will build a dependency tree, and then it will schedule those jobs in the fastest sequence possible to get the work done. Now the images, they are specified by recipes, not by a configuration in your local.conf. So there are recipes called things like core-image-something. So for example, core image minimal is the minimum thing you need to boot up and get a command shell. Core image base does the same, but a little bit more. It adds some functionality, including things like being able to load kernel modules. And then there are more sophisticated images with more and more functionality within them. Typically what you'll do is you will take one of these that most closely matches what you want to achieve, and then you'll modify that to add in the particular packages you need to do your particular job. So to build an image, you just do this. Bitbake core image minimal, and like I say, the builds typically take several hours, so you come back later and you'll find it's built everything. And I should say that when it's doing the build, not only is it just compiling those recipes, the first thing it does actually is to build the cross compiler. So we start off with nothing. We build the cross compilers from source, typically GCC, but can also be Clang. Then we build any other tools required for build time, and only then can we start actually compiling code for the target machine. Oops. So demo, building image for QEMU ARM. This is where it all goes wrong. So bear with me. Right, so I have here a copy of Pocky Kirkstone, which I downloaded earlier. And this is more or less as I showed on the slides. So we have these various meta directories. We have over here oh no, we don't have a build directory because I haven't actually set this up yet. Okay, so we're starting from a blank slate. So I'm going to do dot OE init whatever, and I'm going to call build QEMU. Okay, so that is now put me into that directory. We have the conf directory. If we look in conf, we have BB layers and local.conf and one other random file which I'm not interested in. Now, I need to make a couple of changes to the configuration, so I need to edit conf local conf. And I need to add a couple of things in here, and I've got a crib sheet over here which I'm going to crib from. I'll explain exactly why I'm doing this later on, I think. Oops, what happened there? So I'm setting it a couple of pointers. And then down here, I need to select the machine. So the machine I want is going to be the first one in this list. QEMU ARM is going to be a 32-bit ARM system. I could have chosen ARM64, also MIPS, PowerPC, x86, and there are other things I could add in by adding in appropriate meta layers. Okay, so if everything's done right, I can now type Bitbake core base. And I'll just hang on a second to see if it actually starts up. So if anybody here was on my workshop we did Monday, Tuesday, where we were doing this for the Raspberry Pi, you'll know that I got this entirely wrong. And the builds, which were meant to take about 5 minutes, actually took like 4 hours. I'm hoping this is going to take more like 5 minutes. So you can see now it says parsing recipes. So it's going through all the recipes it's got. It's building a big long list of them and working out dependencies. And now it's working out what it needs to do in order to build the thing I wanted. And see up here it says machine is QEMU ARM. Distro version is Pocky 401. And now you can see it's kind of running through very, very quickly all of the tasks it has to build this. So we'll leave that running for a little while. I'll come back to that in a slide or two. So what I'm hoping we're going to find at the end of this is that, so this is my build directory, which I call build QEMU. And it will have, well, okay, the stuff it downloads in order to build stuff ends up in a directory called downloads. There's a thing called the shared state cache. But the real interesting stuff is in a directory, rather confusingly, called temp, TMP. Only part of it is temporary, some of it is kind of useful. So if you look in TMP, we have a directory called deploy. There's a subdirectory to that called images, and a subdirectory to that called QEMU ARM. So that contains the compiled image, which I can use for my target. The next 3 slides are going through that in slightly more detail. I'm slipping a little bit behind schedule, so I'm going to skip these a little bit. I think it'll become obvious when we see the result, hopefully, of that Bitbake. Let me just say a little bit about these image formats. So when I say Bitbake something image, what actually is going to happen? Well, it depends on the configuration of the machine. So essentially, Bitbake is going to build an image of a format suitable for your target hardware. The kind of formats you're going to have then are going to be things like maybe just a pure tar file. So you can then untar that into an appropriate file system, and there's your root file system. Or you can tell it to generate the root file system in a formatted image format. So for example, ext4, or maybe JFFS2, which is for flash memory, or UBFS, which is another flash format, and various others. In that case, you would just do a DD or equivalent onto your target device. Or you can actually use something called WIC, which is the, actually I don't remember what WIC stands for, it doesn't matter, but it's an image creator which will create disk images, in other words, including a partition table, and you can just DD the entire disk image to the root of a block device, hopefully an SD card, and you can then plug that into your target device, and the way it goes. So just for reference then, these the types of image that are generated for any particular machine are set up in the configuration file for your machine, and you have image FS types, ext3, tarbz2, or whatever. Now, normally this is given to you as part of the board support package for whichever board you're using. You don't normally have to go and edit this stuff. Let me just say a little bit about the shared state cache. So as Bitbake is going through building stuff, it takes a copy of all the build artifacts and puts them into a directory called sstate cache. And the nice thing about this is that once you have warmed up the cache or pre-filled it, you can then rebuild the same thing again much more quickly, because you're missing out the compile stage. You just need to copy the appropriate objects. So that's why it was chugging through really quickly on my laptop. It's not my laptop is particularly fast. It's just that actually I'm cheating a little bit by using a shared state cache, which has already been primed with all the stuff I know we'll need. And you kind of saw when I did that paste from the crib sheet, I was setting a couple of variables. One is called sStateDir, and the other one is DLDir. So I set them to paths which point to preloaded shared state cache and downloads. So hopefully, yes. So coming back here, then we can see that that has all completed. And if I look into the TMP, whoops, TMP, deploy images, QEMU ARM. So these are the images it has generated. The one we need actually for runtime is going to be this ext4 image, because we're going to pass that as a parameter to QEMU. There should be somewhere here, yeah, there's a kernel image, so Z image is Linux, and there's some modules and various other bits and pieces. So I'm going to run that now. I'm going to run, so I can use a command called run QEMU, which is a little script, a little wrapper program. And I'm going to say no graphic, because I just want a text console. So now you can see it's booting up. So that's the Linux boot messages. Now it's starting user space. And now we've got a login prompt. Login as root. There's no password because this is a debug version. So there's not a lot going on here. There is some udev tasks, RPC bind. I'm not exactly sure why we're doing that. There's a log daemon. There's a couple of network configuration daemons and whatever. But apart from that, there's not a lot going on. Oh, and I can prove this is ARM. If we look at proc CPU info and scroll back a little bit. So yeah, it's an ARM v7 processor, and it's emulating a quad-core ARM v7, and it's 32 bits. Okay, so that's got the system up and running. That's told you a little bit about machines and distros and images. So now let's talk a little bit more about these meta layers. The meta layer is one of the most useful things, really, that Yocto gives us. So this is what you see inside your bblayers.conf file. And it's a pretty simple format. It's just bblayers, one of these funny assignment things, and then a list of meta somethings or others. So this is just a directory which contains a layer, a bunch of recipes. And when I want to add to this, essentially, I just need to add an extra line to this file. Yeah, we can characterize layers into three basic types. There's BSPs, there's distros, and there's everything else. So the first bunch then, the BSPs. BSP stands for Board Support Package. So this contains the components, the recipes needed to build Yocto for your particular hardware. So the BSP, at the very least, must contain a configuration file for your hardware. So for the Raspberry Pi meta layer, there'll be a raspberrypi.conf for machine equals Raspberry Pi. In addition to that, it probably will contain some additional stuff. So probably there's some code there's a recipe in there to build a bootloader, maybe a custom kernel, maybe some graphics drivers, or whatever's special about that particular board. Distribution layers define a distro. So at the very least, distribution layers must contain a conf distro and then the name of the distro.conf file. So Pocky is a distro. There's also one called Angstrom. We looked at AGL earlier on, so there's an AGL distro, which is the automotive grade Linux thing, and so on. And then everything else, well, that is everything else. So if it's not a BSP and it's not a distro, it's an everything else. So this can contain libraries, such as Qt. It can contain support for languages, so Java and Python and whatever other languages there may be. And also tools like meta virtualization, which contains stuff for containers and things. Meta SE Linux contains, well, SE Linux. So there is a repository for these layers, and hopefully this is going to work. Here we go. Yes, it does work. So this is the Open Embedded Layer Index. And it lists a whole bunch of layers. I've not counted, but there's several hundred of them. And you can see that they're characterized. So these are BSP layers, and these are for various boards and chips you may recognize, some maybe not. But somewhere down here, for example, scroll on down a bit, we should see Meta Raspberry Pi. Yeah, there it is. So that contains the board support package for Raspberry Pis. And yeah, and so on and so on. And as you can see, there's quite a lot. There's at least 100 of those. Then we have the various distros, including AGL for automotive grade Linux. And I notice Angstrom is here. I think Angstrom is probably not particularly supported anymore, but it's still there. And then way down here we get software. So this is things like, well, whatever. Like I say, there's somewhere amongst this stuff, there's Qt, and there's, I just saw MetaGo go past. I thought Golang, actually I think that's probably out of date. I think Golang is now integrated into the core layers. Anyhow, you get the point. So we use this when we want to add software to our project. So let's do this. So I can select either layers or recipes. Let's choose a recipe. And I can just do a search for whatever it is I'm looking for. So I'm going to take a simple example. Suppose we want to add the Nano editor to our system. So search for Nano, let it think for a little while, and it says, yeah, okay, we have a recipe called Nano. It is a small and friendly console editor, and I can click on this link here, and it gives me a bit more detail. And it should tell me somewhere the layer I should get it from. I guess I get it from Meta OE. So this is part of a layer called Meta OE. So I need to go into, do a git clone of that repository there. That includes the entire Meta OE layer, which I can then, which includes the Nano recipe. So demo adding a layer. So what I want to do then, I've already kind of done the download to make life a little bit easier, but I should be able to quit out of that. And again, I'm going to cheat a little bit, but I just need to go into my, I need to add the layer first, which I should be able to do using this command. So I'm using Bitbake layers, add layer, and then a pointer to the directory which contains the layer I need, which you may remember is called meta-OE. And then, doing the wrong thing again. Yeah, so I can now run this command here just to show that the nano recipe is available. Do that. Yeah. Unfortunately, whenever you do something, it rebuilds the dependency cache, which takes a moment or two. And then I just need to add the a thing to the to my local.conf that will include the nano recipe. So I was just stumbling there because I was looking at the time and I was just trying to remember what time I finish. I think I've got a few minutes left yet. So when you're doing stuff with Yocto and Open Embedded, it's really important to have some kind of hobby, such as playing chess or yoga or meditation, anything that you can use to fill in the gaps while you're waiting for things to happen. If all else fails, you can always fall back to sword fights on office chairs, as popularized in the famous cartoon. Okay, right, so that finished, and you can just about see here, we now have a matching recipe, and it's in that directory there, and it's nano version 6.2. So I want to add that to my QEMU build. So conf, local conf, and again, I'm going to use a crib just to make sure I don't get it wrong. So I've added the text in here, image install :append equals space nano in double quotes. I will briefly explain what that means later on, but for the moment we can be happy, I think, that image install is a variable, it's a Bitbake variable, and it's basically a list of all the recipes it's going to build. The append operator is going to add to the end of that list. So we're just adding nano to the list of recipes that Bitbake is going to build for me. So I should be able to do if I do it right. There we go. I just do a Bitbake core image base. It shouldn't take so long this time. I mean, it took maybe 3 or 4 minutes last time, so I'll probably hang around just to see it work. And again, this is going to work quite quickly because I've done this previously, about an hour ago, in fact, just to make sure that the shared state cache was up to date. Yeah, unfortunately, whenever you change any file anywhere, it seems to go through and regenerate the shared state cache, but hey, that's it. Okay, I'm really going to wait for this, so apologies. Okay, so now it's burst into action. And it very quickly obtained the nano packages from the shared state cache. And now it's doing a task called do root fs. So this is assembling the root file system from all the various components that we've specified, including nano in this case. And when this is finished, I can just do a run QEMU. Boots up. Log on. And hopefully I can now go nano. Oops. And I guess Control X works. Yes, good. And there we go. So, hey, we can create text files and edit them using Nano. Probably not that useful in the grand scheme of things, but it was a good little demonstration, I think. So hopefully then you get this idea about layers containing recipes, and then we add recipes by essentially adding a dependency on that recipe, which we did in this case by using that image install append syntax. So for the final section, yeah, we can do this. I need to talk a little bit about recipes. So I want you to see what a recipe is, at least in principle, and yeah, we'll try adding a recipe of our own. So a recipe contains the instructions on how to fetch, configure, compile, and install a software component. So this can be a library, it can be an executable, it can just be a script or a configuration file. It doesn't have to have the compile stage if you don't want to actually compile it. At the base, a recipe is a list of tasks. And tasks are called things like do, compile, or do install or something. Generally speaking, you don't need to specify every single task in every recipe because you will inherit behavior from Bitbake, which will fill in most of the tasks with defaults. So you just need to add in overrides for the things that are special for your recipe. So here is a simple recipe, and this is going to build a Hello World program for us. So we start off with some just human readable description stuff. These first two lines are not strictly speaking necessary, but they're handy. Then we have some stuff to do with licenses. So it's a build error not to specify a license. Everything has a license. So in this case, we have an MIT license. And not only do you need to say what the license is, you need to give a pointer to the text of that license and also a checksum of that text. So you can't cheat the system. You have to have an actual license with an actual checksum. And it's a build error if none of that works. Then we have source URI. So the source URIs is a list of places to go get things. In a more realistic case, the source URIs would be web addresses or Git archives or something. But in this simple case, we are using a local file MIME type. So this is going to go and grab a file called helloworld.c from within, actually it comes from within a directory called files in the directory that contains the BB file. Then we have do compile and do install. So these are the special things that we need to do for this recipe. So do compile is going to compile hello world and output an executable called hello world. And then do install is going to install that executable into $bindir. So $bindir is going to work out to be user bin. So we create the user bin directory here, and then we install the executable into that directory. Now, when you build a recipe, it will generate packages. And this is a thing that's not particularly well described in the open embedded documentation. And even the developers tend to misuse these terms, in my opinion. So just be clear, a recipe is something .bb, it's a file. But the packages it generates are multiple. So this is a case of a library, libz, which is the compression library. You get in this example at least, you get 6 different packages. You get the runtime, which contains the .so file. You get the debug, which contains the .so file with debug symbols. You get the dev, which contains the header file. You get the doc, which contains basically the man pages. Actually, nobody cares. You get the source. So that's handy for debugging because you need the source code if you're using source level debugging. And you get static dev, which nobody ever uses, but that includes the .a file, the archive, if you want to statically link against libz, which probably you don't want to do, but you can if you want. So the point is then, a single recipe typically generates multiple packages. And notice these are in a format called RPM, the Red Hat Package Manager. It's just a standard container for for packages. And then to add a package to our target, there are multiple ways of doing this. The way I'm doing it here is using this image install variable. So we have things like image install append, and we can give a list of packages, in this case dropbear, which is an SSH daemon, and lightttbd, which is a little web server. There are other ways of doing it, which I'm not going to differentiate with right now. And notice we're using a different syntax for adding here than here for obscure reasons, which I'm really not going to go into. So, final demo, then I'm going to add that hello world to my Yocto. Okay, so the first thing I need to do actually is to create a layer, because recipes live within layers. So I want to create my own layer where I can put this stuff. And again, if I just crib this, I'm going to call my layer meta example. So I do that. So Bitbake layers create layer. Oh, I've missed the E off, never mind. And actually it tells me what to do next. It says I need to add Bitbake layers, add layer, meta example without the E. Hoping that works. Yep. So now I have, I go up a level, meta, whoops, example, and that contains a configuration file. You also get for free a recipes dash something, which contains a does nothing recipe. So I'm just going to copy and, oops, why isn't that there? Yes, I thought it was in this directory. Did it end up the directory? Should be here. Okay, this is going somewhat wrong. Oh well, okay, we can do it the hard way. If I go into meta example space, actually I can cheat. I know I've got a copy hidden away somewhere. Bear with me, it's a fairly long path name. Solutions, I think. Oh no, recipes. Yeah, do it. Why not? I forgot what to say. Thank you. There we go. So there's my hello world. Just run a tree. Oh, I'm in the wrong directory. That's the problem. Oh dear. Okay, demo effect. Example. No. Dot. Yeah, okay. So now I've got hello world files. There's the hello world C file, and there's the recipe. Okay, so cd $build here. Go into conf, local conf, and then head down here. And then do a Bitbake. Okay, and that is now going to pick up my recipe, I hope, and add a hello world program to my target. Come back to that in a moment or two. Pretty much done. I'd like to add a couple of minutes for questions, although we're running out of time a little bit. Conclusions. Well, so Yocto Project is industry standard. Pretty much anybody doing embedded Linux systems is going to be using Yocto at some point or other. Good things about Yocto Project is, first of all, it produces reproducible builds. So because we're building from source code each time, we know that when we do the build, we know exactly what's in the build. We know the ancestry of every single component. It gives us a license manifest, because all this license stuff we kind of looked at. So you can just run a command and it dumps out all the licenses you're using. And it can also generate a software bill of materials, an SBOM, which is becoming more and more important as we want to track the ancestry and the dependencies we have on a particular project. Layers, key concept, allows us to add recipes from third parties and also scales well to large teams. We can have multiple teams, each working in their own layer, and then they don't tread onto each other's toes too often. Finally, I haven't mentioned SDKs at all, but you can generate an SDK from Yocto, which is essentially just the cross compilers and necessary libraries. And you can then give that to the people in your project who don't really care about Yocto and don't need to know about Yocto, but simply want to write applications in Qt or whatever for your target product. So a quick look, see if my build finished. Do a run QEMU. Why isn't it there? No. I think. And the major thing that's going to happen is I'll type hello world and it will say hello world. But hey, I would say that hello world is kind of the gateway drug for programmers. If you can write hello world, you can write any program anywhere. So that's why we always start by writing hello world. There we go, it worked. So thank you all very much. We have pretty much zero time for questions. I'm sorry about that, but we could maybe squeeze a couple in. Slides are available here. You can contact me via Twitter or Twittin if you like, at 2Net Software, and you can link with me on LinkedIn. So we have time for maybe a couple of questions without intruding too much onto the next thing. So any questions? Very quickly. Oh, we're all totally overwhelmed. Yes, sir. Tricky question. So the question is, if the board support package I'm given has a vendor kernel in it, can I replace that with a mainline kernel? Not really. So it all comes down to the board support package. So the BSP recipe you have will, amongst other things, define the Linux kernel it's going to use. So if you get a recipe for an NXP IMX8, then that will use the Freescale kernel. If you get a recipe for Raspberry Pi, that will use the Raspberry Pi kernel, and so on and so on. So generally speaking, the vendor kernel comes as part of the deal. Okay. Okay, question. If I use if I put the shared state cache onto an NFS server, as I kind of hinted in the slides, can that mess things up? And I guess the simple answer is yes. It can definitely mess things up. If you do things right, you can keep the cache clean, and you can, everybody can, who's using that file can benefit from it. But there are, if you look at the mail list, one of the most common questions on the mail list is, how do I set up my shared state cache correctly so it doesn't screw up? So I'm just going to say that yes, it is a potential problem. If you do it right, it's a huge benefit. But if not, you can waste a lot of time regenerating the cache because someone somewhere has messed it up. Sorry, I can't go into more detail than that just now. Yes, sir? Yeah, okay. So I kind of skipped over that a little bit when I talked about the licensing. So everything must have a license. With closed source code, you have basically two options. You can use a license type called proprietary, and then you just give the text and checksum of the license file. So this assumes you have the license files as a text file that's accessible to you. Or you can set the license to be closed in uppercase, which means you don't have to have a license file. So either way around, you can supply either your own license, or you can just put closed, which says this is closed source, and the license is defined somewhere else. Okay. Okay, two more, and then we'll finish. So, you, sir? So do you build in a container, or do you build native on Linux? Probably is worthwhile putting it into a container so you can. So I mean, the build system is sensitive to the operating system it's running on top of. So typically, the Yocto developers support the 3 most recent versions of Ubuntu, SUSE, CentOS or something, I don't remember the exact list. But if you are trying to build an older version, which is using an older operating system, which you may not have available to you, then yes, a container would help you avoid some of those dependencies. Okay, last question. There is so it's not built, so the SBOM is not generated every time you do a build. There is a special thing you do, and off the top of my head, I can't remember what it is, to cause it to spit out the SBOM. So yeah, it's on demand. Okay, so thank you all very much for listening to me. Hope that was in some way useful. And I shall be doing a further talk on embedded Linux in about 15 minutes' time. So thank you all very much.